general relativity, step by step. We've got the Einstein field equations here, which link on the left and right hand sides two second rank tensors. And it looks like there are 16 equations here. But there aren't. There's only 10, because if I write it out as a matrix, we know that both the left and the right hand side are symmetrical. We know that the fundamental tensor G alpha beta is symmetric, and we know that the Ricci tensor is symmetric as well, and we will also of course know that the stress energy tensor is symmetric. So not all of these are independent of each other, and we only need to consider these 10 terms here. These 6 here are just reflections of the guys above the diagonal. So the Einstein field equations, it looks as though they've got 10 degrees of freedom, or there's 10 independent equations. You normally talk about degrees of freedom, but they don't. If they did, they would allow us to predict the metric tensor as a function of time, writing here, as a function of time and of course position. We could extract from the field equations those 10 independent elements of the metric tensor. And this cannot be right, because if it did, it would remove the freedom that we have so carefully set up to choose the coordinate system how we wish. So 10 degrees of freedom in the equations, in Einstein I guess, in the Einstein field equations, are enough to pin down, subject to appropriate starting conditions, to pin down all the elements of the metric tensor for now and forever. Forever. And that can't be true, that can't be right, because some people might want to use a nice Cartesian, even in two spatial dimensions you can see this isn't going to work. Whereas some people are going to want to consider a nice radial system, and other people are going to consider want to consider some weird arbitrary system here. And if the Einstein field equations included 10 degrees of freedom, that would curtail our freedom to choose the coordinate system that we want. If we think about a coordinate transform x bar, let's consider x0, x1, x2 and x3, and I want to transform to x, so this is like a transform from there to there. X bar 1, x bar 2, x bar 3. Well, I might say that x bar 0 equals f0 of x0 through x3. X bar 1 equals f1 of the same things. Oops. X bar 2 equals f2. And of course x bar 3 equals f3 of the same things. So this tells me that a coordinate transform has 1, 2, 3, 4 degrees of freedom. So we need to maintain 4 degrees of freedom for us humans to choose a coordinate system that we find easy or appropriate or natural or something. But there's nothing fundamental about any coordinate system. That's the whole point of relativity. You can choose your coordinate systems arbitrarily, and this is why we needed to go through all this crazy stuff with Christoffel symbols and covariant differentiation and all the rest. So the Einstein field equations cannot possibly have 10 degrees of freedom. They must have 10 minus 4 equals 6. Actually, they could have fewer than that. We might need other equations to close the system. But I'll ignore that issue for the moment. The Einstein field equations must have 6 degrees of freedom. So how can that be? How can we possibly have a system that looks like it's got, well, here it is. It looks like it's got 10 degrees of freedom, but it can have only 6. And the answer is that we have embedded into our thinking of this equation, we have embedded into this equation the conservation of mass energy, and we also have embedded into it the we spent a great deal of time ensuring that this is true by making sure that the covariant divergence of the Ricci tensor was also equal to 0, which was effectively the Bianchi identities, or via the Bianchi identities. And of course, there's 4 degrees of freedom in these restrictions here. And so another way of, and that 4 is accounting for the difference, it's this 4 here. So the Bianchi identities and the conservation of mass energy give us 4 degrees of freedom, which is exactly enough to account for the 10 degrees of freedom that the Einstein field equations have got, and the 6 degrees of freedom that they are allowed to have. They can't have more than 6 degrees of freedom because you need coordinate independence. It's a tricky and subtle issue. There are ways to sort it out, there are ways to think about it. The way I prefer to think about it is that the Einstein field equations, let me find them, the Einstein field equations are 10 equations on the pair alpha, beta, and the stress energy tensor. We've got a pair of tensors here which have between them 20 degrees of freedom, I guess, but we are placing 10 degrees of freedom, or we're placing 10 restrictions on this pair of physically meaningful tensors here. And that's how I prefer to view the Einstein field equations, as a restriction on the pair of tensors, metric tensor and the stress energy tensor. Numerical solution of the Einstein field equations is very, very difficult. It's very, very, very involved. And not least of which is that you need a coordinate system of some type. It's an arbitrary one, of course, but we need a coordinate system of some type in order to describe how the stress energy tensor varies with space and time. So you're pinned down straight away to an arbitrary coordinate system, and that pinning down does not sit well with the conceptual freedom from specific coordinate systems that relativity, general relativity, provides. So I'm just going to leave it there. I guess the take-home message of this screencast is that the Einstein field equations are hard. Stop there.